Welcome to Study Loop.
Take a look here at utilizing the periodic table to do some orbital configurations or diagrams for some metal cations. So first example is going to be for chromium 3+. So as we follow the periodic table and fill the electrons properly, first row of the periodic table, we fill the first two electrons in the structure in the 1s subshell with its one orbital. And then in the second row of the periodic table, we have both the S and P subshells that we can utilize here. So we're going to completely fill the 1 orbital in the 2s subshell and the 3 orbitals in the 2p subshell. Then we move on to the third row of the periodic table where we have the same basic process. We completely fill the electrons in both the 3s and 3p subshells. Notice here that the chromium is in the fourth row of the periodic table. So first we fill the 4s subshell, but then something new happens. We introduce the d subshell in that fourth row of the periodic table, and it's specifically the 3d subshell. And so if we follow the structure here for chromium, it would appear that we're going to add 4 3d electrons. But here's the deal. And each one of them would occupy, by the way, its own orbital. And there are 5 orbitals in the 3D subshell. But chromium follows as an atom and anomalous configuration. And it borrows one of those 4s electrons to completely fill all 5 of the orbitals in the 3D subshell. So as an atom, the 4s, there is just 1 electron in the 4s subshell, 5 electrons in the 3D subshell. Now, if chromium becomes the +3 cation, we need to lose the 3 highest energy electrons to accommodate that. The first electron comes from always the highest number shell. So the first electron will come from the 4s subshell. The 2 remaining electrons that we need to lose in order to become the +3 cation, doesn't really matter which of the electrons in the 3D subshell we choose, but we just need to choose 2 of them. And the question here is, is the structure then for chromium as a +3 cation paramagnetic or diamagnetic? Where paramagnetic means somewhere we have at least one unpaired electron in my orbital diagram, and diamagnetic means all of the electrons are paired. Well, it's pretty clear here that we have 3 unpaired electrons, and therefore the chromium +3 cation would be paramagnetic in its structure. Now we're asked also to look at making an orbital diagram and determining whether vanadium as a 5+ cation is dia or paramagnetic in a similar way to what we did with the chromium example. So vanadium is going to be located right here. It's going to follow a very similar, again, atomic configuration as chromium. And just recognize here that we're going to fill up the same subshells in the same order until we reach that 3D subshell. And at that point, we notice that vanadium just has 3 electrons to place, one of each in one of the 5 orbitals in the 3D subshell. And now to become the +5 cation, so this is the atomic configuration for vanadium. To become the +5 cation, we first lose the 2 electrons that come from the highest number 4s subshell, but we still need to lose 3 more electrons to become the +5 cation. And look at the structure that we're left with then. All of the electrons are paired in the remaining subshells. Therefore, vanadium in a +5 cation form is diamagnetic. Next, we're going to take a look at nickel 2 plus. So nickel's located right here in the periodic table. And yeah, you guessed it. A lot of the same pattern that we're going to follow in making first nickel in its atomic form and then nickel in its +2 cation form. So it too is going to have completely filled subshells all the way up through the 4s subshell. And then when we reach that 3d subshell, we end up needing 8 electrons in the 3d subshell. So we start by placing 1 electron in each of the 5 orbitals and then start pairing up orbitals until we reach 8 electrons. Now in its +2 cation form, nickel again, like the other species before it, is going to lose that highest number 4s subshell before doing anything with any of the 3d electrons. So if we were to look at the orbital configuration for nickel 2 plus, notice that we have 2 unpaired electrons that exist in the 3d subshell. And anytime we have unpaired electrons anywhere in the configuration, that species is paramagnetic. So the final example we're going to take a look at is iron 3 plus. It too is located in the 4th row, utilizing that 3D subshell. So same pattern we've been following, where we completely fill all of the subshells through the 4s subshell. So far so good. And when we reach the 3D subshell, notice that iron is going to have, I'm going to count them, try to count them this way, 2, 3, 4, 5, 6 electrons that occupy the 3D subshell. So we place the first 5 in their own separate orbitals, and then we have to pair up one of the orbitals in the 3D subshell. Now to make the +3 cation, as always, we remove the 4s subshell electrons first, and then we need to remove one of the electrons from the 3D subshell. So we're going to remove one of these paired electrons to sort of free up the 3D subshell. And the bottom line is that I'm still going to have 5 unpaired electrons in the overall structure. So anytime again I have unpaired electrons, the structure is paramagnetic.